Hello, everyone. So we will continue with the conservation of energy. And as you can see in this slide, we've seen that the gravitational potential energy and kinetic energy for the first state should equal any other states within the motion that's happening to the object that we're evaluating. So the energy is conserved. However, it changes from one form to another. So if we look at this graph, we can see that our reference here, the ground, this is where y equals to 0. And right at this point, when the sphere wants to slide, at this point, the velocity is 0, and that's why the kinetic energy is 0. He or she has 50k joules as a potential energy. Once it slides, then the kinetic energy increases and the potential energy, the gravitational potential energy decreases till it reaches this point, and then it continues till it reaches the ground. At the ground, the potential energy, right before it hits the ground, potential energy becomes 0, and the kinetic energy would be maximum. Now let's look at this example where basically in this example we have a diver starts from rest at 13.6 meter above the surface of the water. So our reference is the surface of the water. This is our reference where we consider y equals to 0. What is the diver's speed when he is 3.4 meter above the surface of the water? Solve this question using the principle of conservation of energy. So in this case, we have the diver at 13.6 meter above the surface of the water, which is my reference, y equals to 0. I want to find the speed when he reaches this point, which is 3.4 meter. So we will be using the conservation of energy to solve for this problem. As you know by now that the kinetic energy here, K, the EK, let me call this one EK1 plus EP1, and here I have EK2 plus EP2. Those are equal. So right at this point where he's starting from rest, we know the velocity here is 0, and we know y is 13.6 meter. So if I start first with the EK1 equals to half mv 1 squared, and this, as I said, equals to 0. Then I have EP1, that is mgy1. I don't know the mass, so EP1 equals to 9.8 times 13.6 m, so joules. And the answer for this is AP1 equals to 133.28 joules. For the second case, I know EP2 equals to mgy2. EP2 equals to 3.4 times 9.8 m, which is 33.32 m joules. EK2 is half V2 squared, and this is what I want. Now applying the conservation of energy, which is EK1 plus EP1 equals to EK2 plus EP2, gives me, this is 0, EP1 is 133.3 m equals to EK2 half m V2 squared plus 33.32 m. Then I can cancel the mass, and V2 after rearranging would be 14.14 meter per second. So this is how we can apply the conservation of energy in order to calculate the velocity right at that point. Now let's look at this example. In this example, we have an apple that is 1 meter above the ground, call it apple A, and apple B that is 9 meters above the ground. So my reference here is the ground. How does the speed of apple B compare with the speed of apple A when they reach the ground? So we need to calculate the relationship between the ratio between the both velocities once they reach the ground. Assume that they start from rest when they fall. Okay. So we have apple A, apple B. One of them is 1 meter. B is 9 meters above. A is 1 meter above. We need to calculate the ratio between both velocities once they reach the ground. This is apple B. This is apple A. This is my ground, the reference, y equals to 0. This is 1 meter. This is 9 meters. Okay, so let's start first with apple B. I know that for apple B, K, EK, EKB, I, plus EP, for B initial, equals to EK for B final, plus EP for B final. So starting from rest, which means that the kinetic energy is zero because the velocity is zero, then the gravitational potential energy is mg, let me call this one mb, 9 meters, equals to the potential energy right at the final would be zero because y now is zero. Then the kinetic energy would be half mb v b final square. So mb will cancel. Then I have 9.8 times 9 equals to half vf squared. Now the same thing for A. Also, the kinetic energy right at the initial is zero, and the potential energy right at the surface of the ground would be zero. So I will use MA G Y is 1, right? Because we know that EP is mgy. So y for B is 9 meters, y for A is 1 meter, equals to half MA VA final squared. MA is going to cancel, and then 9.8 equals to half VA final squared. Now, if I divide this by this, what do I get? If I call this one 1 and this one 2, divide 1 by 2, so 9.8 times 9 divided by 9.8 equals to half VBF squared divided by half VAF squared. The half is going to cancel. 9.8 also is going to cancel. Now take the square root for both sides. I get VBF divided by VAF equals 3, which means that the velocity for the apple B would be 3 times the velocity of the apple A. And this is expected because apple B is higher than apple A, which means it will face, it will have higher velocity once it reaches the ground because the distance is longer. Okay. Now, so the answer is A. VB is 3 times VA. Now let's look at our last example here. In this example, you throw a baseball with a velocity of 2.5 meter, as you can see here, with a 15 degrees above the horizontal. The ball leaves your hand with your hand 1 meter above the ground. So this is my ground. This is my reference, y equals to 0. Use conservation of energy. So once you read use conservation of energy, you have to do what we have done in terms of kinetic energy, gravitational potential energy between two positions, making the energy equal, the total energy equal. However, the kinetic energy, potential energy will be different, but the summation of both will be the same. Use conservation of energy to determine the ball's speed just before it hits the ground. So what do I know? I know the velocity. I know the height of the ball. And I know how far, I know my reference here. So if I am to calculate this, then we know this is the ball. This is my reference, y equals 0. This is the height, 1 meter. Velocity, it is 2.5 meter per second. Angle 15 degrees above the horizon. We need to calculate the velocity right here. So if I call this one V initial and this one VF, and use the conservation of energy, where basically I need to calculate the EK and the EP at this point, and the EK and the EP right at this point as well. So let me start first with the EK I equals 2 half m VI squared. So EKI is half m 2.5 squared. EKI is 3.125 m. Right? And then EPI is mgy API M times 9.8 1 API is 9.8 M joules. Now right at this point I have EPF equals 0, y 0, because now y here is 0, mgy, y is 0, so EPF is 0. EKF is half mbf squared, and this is what we are after. We don't know the mass, so then I have EKI plus EPI equals to EKF plus EPF. So we said EPF is 0. Substitute EKI with a 3.125 M. Substitute EPI with 9.8 M equals to EKF, which is half M BF squared. Again, M is going to cancel. Then BF squared is 3.125 plus 9.8 times 2 is 25.85, and VF is 5.1 meter per second. This concludes our lecture.